The question we have today is you're standing on the earth, you throw a small rock with a mass 0.5 kilograms into the air. At the instant it leaves your hand, the rock's velocity is 0.1, 4.0, and zero point 0.3 meters per second, respectively, in the x, y, and z axes. Here, the y axis is vertical and the x axis horizontal. You may ignore the force of air resistance. What is a rock's initial momentum just after it leaves your hand? Express your answer as a vector. Now, what they have given us is the mass, that is zero point 0.5 kilograms, and the v initial, that is zero point 0.1, 4.0, and zero point 0.3 meters per second in the x, y, and z components. We know that the initial momentum is mass times the v initial, and that's what I've done here. So it's technically zero point 0.5 times 0.1, 0.5 times 4.0, and zero point 0.5 times zero point 0.3, which accounts to 0.05, 2.0, and 0.15 kilogram meters per second in the x, y, and z axes. Now we have a second part for this question. What is a rock's momentum 0.25 seconds after it leaves your hand? Start from a fundamental principle. Express your answer as a vector. Now, when they say a fundamental principle, what they are looking for is the momentum principle, which states that the initial momentum minus the final momentum is force times delta t. Now we already know the p initial that we have calculated right over here, and the force. Now we know that the air resistance is negligible, so air resistance is so the force acting on the x component is zero, and the force acting on the z component is zero since nothing is mentioned about it. And in the y component we have gravity acting on the rock. So now don't forget to put a negative sign, that is mass times the gravitational constant. Not I mean not the gravitational constant, mass times g, mass times the constant g, which stands for 9.8 newtons. So we have minus zero point 0.5 times 9.8 acting in the y component. Our p initial is 0.05, 2, and 0.15. Now we're going to rearrange this formula here to make it look like final momentum, which is what we're trying to find, is equal to the initial momentum plus force times delta t. Now, for simplicity, what we're going to do is we're kind of going to take it in the x-axis, y-axis, and the z-axis separately. So in the momentum in the x-axis remains the same since there's no force acting on it. So since there's no force acting on it, this part of the equation will be zero. So the initial momentum will equal the final momentum, and that is the case for z-axis also. So it is 0.05 kilogram meters per second in the x-axis, and in the z-axis is 0.15 kilogram meters per second. Now in the y-axis, we have a force acting on it, that is minus zero point 0.5 into 9.8, which is equal to minus 4.9 kilogram meters per second acting on it, and the time is 0.25, that is the delta t. So we calculate that and we get 0.775 kilogram meters per second, which is the answer we are looking for. So the final momentum is what we see here, that is 0.05, 0.775, and 0.15 kilogram meters per second in the x, y, and z axes. Now, as I mentioned earlier, the fundamental principle they're looking for is Pf minus Pi is F delta T. Thank you.